Hello everyone. In this video, I'm going to show you how to do the homework on probability distributions. So for the first few questions, we have the experiment of flipping a coin 5 times, and there are 32 possible outcomes, which I've given you the list of here, and these are all equally likely. So we're asked to make a probability distribution in the form of a table for the number of tails, and use your probability distribution to calculate the expected value of the number of tails. So we're going to fill in this little chart here. So on the left column, we want to put the possible numbers of tails. So you can have 0 tails, 1 tail, 2 tails, 3 tails, 4 tails, or 5 tails. And then the probability of each of those depends on how many outcomes in this table have that number of tails. So I'm actually going to go through this table and just write the number of tails in each cell. I think that's the easiest way to do it. So this is 0 tails, this is 1, this is 1, 2, 1, 2, 2, 3. So I'm just going to go ahead and do this and speed it up. Okay, so I've written the number in for each possible outcome. So now I want to know how many outcomes are there with 0 tails out of these 32, and there's only 1. So the probability of getting 0 tails is 1 out of 32. For 1 tail, how many of these have a 1? There's these two, 1. There's this one, 3, 4, 5, and I think it's just those 5. So that's 5 out of 32. How many outcomes have 2 tails? Let's see, there should be a lot more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 outcomes that have 2 tails. And then for the rest of these, I already know they should be symmetrical because the probability of 3 tails is the same as the probability of 2 heads. This 3 tails is 2 heads, and heads and tails have the same probabilities. So I'm actually just going to fill in the rest of the table symmetrically like this. Okay, you could get the same answers by actually counting, of course. And I'm not going to simplify any of these because that will make it easier to add up the total over here if they're still over the same denominator. Now I'm going to multiply each number by its probability, and that will give me what I need to add up for my expected value at the bottom here. So remember, when you multiply a number times a fraction, you multiply it by the top of the fraction. So this is 0 out of 32, 1 times 5, 5 out of 32, 2 times 10, 20 out of 32, 3 times 10, 30 out of 32, 4 times 5, 20, 5 times 1. Okay, and now since these are all over the same denominator, I'm just going to add up the numerators. So let's see, 5 plus 20 is 25, plus 30 is 55, plus 20, 75, plus 5, 80. So this is 80 over 32. And now we can simplify. If we cancel an 8 from the top and the bottom, then I think it becomes 10 over, what's 32 divided by 8, 4. And then I guess we can still take out another 2 from the top and the bottom, so that's 5 over 2. And 5 over 2, I can do that one in my head. That is 2.5. Now, does this make sense? We flipped a coin 5 times, and this is saying the number of tails that we would expect to see on average is 2.5. Yeah, it's half of the times that you flipped, like half of the coin flips, basically. So that does make sense because heads and tails have half and half probability. So we should see, on average, half of the flips should be tails, 2.5. Okay, in fact, you could actually work that out without doing all this work. But we're doing this for practice. Okay, now let's try using our probability distribution to answer some questions. What is the probability that when flipping a coin 5 times, you get 3 or more heads? So 3 or more heads is going to be, we need to interpret that in terms of tails. So 3 heads is 2 tails, 4 heads is 1 tail, and 5 heads is 0 tails. So actually what we want to know is probability of getting 2 tails or 1 tail or 0 tails. And to get that, all we need to do is just look in this chart here and just add up the probability on each of those lines. Since these rows are mutually exclusive, they cannot the event described over here cannot happen. No two of these numbers of tails can happen at the same time on the same 5 coin flips. So these are mutually exclusive events in each row, so we can just add up their probabilities. So this is going to be 1 over 32 plus 5 over 32 plus 10 over 32. So that is 16 over 32, which is exactly 1/2 or 50%. So the probability when you flip a coin 5 times that you get 3 or more heads is actually 50%. If you think about this for a second, it actually should make sense because getting 3 or more heads means that the majority of the flips were heads, and you must get either majority heads or majority tails, and those two things have to have the same probability. So you either get majority heads or majority tails, and it must be 50-50 because there's no difference between heads and tails. Okay, let's do the last one for this section. What is the probability that when flipping a coin 5 times, you get an odd number of heads? So the odd numbers of heads are going to correspond to, again, we have to interpret this in terms of the tails. So we could get 1 head, and that would be 4 tails. We could get 3 heads, which would be 2 tails. Or we could get 5 heads, and that would be 0 tails. So actually, odd number of heads means even number of tails. So we want the probability of any of those 3 things happening. So 4, 4, 2, 4, 0 tails. We're just going to add them up. So we're looking at this row, and this row. So 1 over 32, 10 over 32, and 5 over 32. Actually, it is 16 again. So this is going to be, let me add them in the right order here. 5 over 32 plus 10 over 32 plus 1 over 32. Again, we get 16 over 32 or 50%. This one is maybe a little bit harder to convince yourself that you could have worked this out without making the chart at all. But if you think about it, since the number of heads and the number of tails have to add up to 5, one of them must be an even number and the other one must be an odd number in order to add up to 5. So whether you get the odd number of heads or the odd number of tails, one of them must be odd. And again, there's no difference between heads and tails. So the fact that this comes out 50-50 actually makes sense. Okay, let's do the next section. Tetrahedral dice have 4 sides each. Tetrahedron is a 3-sided, or it's a pyramid with a triangular base. So it has 4 sides. And here is a table showing the 16 possible outcomes from rolling a pair of tetrahedral dice. So they only go from 1 to 4 instead of 1 to 6. Make a probability distribution in the form of a table for the sum of the 2 dice and find the expected value of the sum. So once again, I'm just going to go through this table of outcomes and just figure out what the sum is in each cell and use that to help me. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. I'll just keep going like this. Okay, so now I have filled in all the sums, and I can see that the different possible values are 2, 3, 4, 5, 6, 7, and 8. And the probability of each one is going to be out of 16. So there's only one that has a sum of 2. So 1 out of 16. There's 2 that have a sum of 3. They appear on the diagonals again, or the anti-diagonals. Usually for a matrix, we say the diagonals go from the top left to the bottom right, like this. Okay, there's 3 that are 4. So 3 out of 16. And then 5, there's 4 of those ones. And then it starts going down again because we passed the widest point. So for 6, there's 3 out of 16, 7, 2 out of 16, and 8, 1 out of 16. Okay, so it's symmetrical probabilities again. All right, now we're going to multiply together the entries in these 2 columns. So again, you just multiply by the numerator. So 2 times 1 is 2, 3 times 2 is 6, 4 times 3 is 12, 5 times 4 is 20, 6 times 3 is 18, 7 times 2 is 14, 8 times 1 is 16. We're kind of getting to the point where you might like to have a calculator, but I think I can still do this. Let me see. Okay, so 2 plus 6 is 8, plus 12 is 20, plus 20 is 40, plus 18 is 58, plus 14 is, let's see, 68, 72, and then plus 8 is 80. I think I did it right. Let's see if the answer ends up making sense. So if I take a factor of 8 out of the top and the bottom, I should get 10 over 2, which I can reduce to 5. Okay, this makes sense to me, that the average would be 5. And the reason it makes sense is because 5 was like the center number here in the table, and the probabilities on each side of it were like balanced. So the center was at 5, and then there were these 3 out of 16 entries pulling it down to 4, but another 3 out of 16 like balancing out by pulling it up to 6, and then the same kind of like balancing situation here with the 3 and the 7 and the 2 and the 8. Whenever you have a symmetrical probability distribution like this, and these are all like equally spaced, then it will come out to just be the middle one. Not that you need to know that. I'm just throwing in like random math knowledge. I like how everything is fit together. Okay, so the expected value was 5. Your expected value, remember, is an average, so like it definitely has to be, it cannot be outside of the range of the possible sums. It has to be between 2 and 8. Okay, so we did that. And now we're going to do the same thing basically, but we're just going to find the minimum of the 2 dice values. So the smaller of the 2 numbers. So this one is going to be 1. This is also 1. This is 1 again. This one is 1. This one is 1. Now the minimum is 2. And again 2. Again 2. Okay. This one is 1. This is 2. This is 3. 3. And 1. 2, 3, and there's only one where the minimum is 4, and it's that one. Okay, so the possible values for the min are 1, 2, 3, and 4, and the probabilities are, so there's 1, 2, 3, 4, 5, 6, 7 entries that have a minimum of 1, so that's 7 out of 16. There's 1, 2, 3, 4, 5 entries with minimum 2, 2 out of 16. There's 3 that have a minimum of 3, and there's 1 that has a minimum of 4. So now we don't have a symmetrical probability distribution, then it becomes harder to predict what the expected value should be. Okay, so now min times probability, 1 times 7, 2 times 2, 3 times 3, and 4 times 1. Okay, and adding all these up, 7 plus 4 is 11, plus 9 is 20, plus 4 is 24. Okay, and if I take a factor of, let's see, 8 out of the top and the bottom, this will be 3 over 2, which is 1.5. Or you can use a calculator. Okay, so I don't really have any particular way to justify that this is 1.5, but it's a number that's between the min and the max, so yeah, that seems fine. All right, let's look at the last section here. Oh, this has ended up aligning like a little bit weirdly. I wonder if I can clear this. Okay, let me pause and do this. Okay, there we go. Microsoft Word was fighting me again. At a certain golf course, the probability distribution for the number of strokes it takes for a randomly selected player to complete the first hole is shown in the chart. If you've never played golf, it's like the number of times that you hit the ball. So hitting it a smaller number is more, it's better. Okay. Oh, this is supposed to say par, not part. Sorry. Par is 3 strokes. So that's like, usually par is the average, or it's like what they would expect someone who has like an average amount of skill to be able to do. So par is 3 strokes. What is the probability that a randomly selected player takes exactly 3 strokes on the first hole? Okay, so we can just read this off the chart here. When the number of strokes is 3, the probability is 25%. So this is 25%. Very easy. Okay, now they get a little harder. What is the probability that a randomly selected player does better than par? So less than 3 strokes is better. So less than 3 strokes is 1 stroke or 2 strokes. So 1 stroke probability is, so I tried to make these hit the exact little lines on here that are at each integer of probability. So this is 1%. And then 2 strokes is 10%. So we just add those together. So less than 3 is 11%. Okay, and then the last one, what is the probability that a randomly selected player does worse than par? Okay, so more than 3 strokes. So we can add up these columns for 4, 5, 6, 7, or 8. Or another way you could do it is these all have to add up to 100%. So we could start with 100% and then subtract the last 2 answers. Either way should get us the right answer. I'm just going to do it the more straightforward way, I guess. So 4 strokes, 5 strokes. Why is it putting all these extra line breaks now? 6 strokes, 7 strokes. Just put them all on their own line. And then 8 strokes, and then I'm going to total them. Total. Okay, so 4 strokes looks like 40%. 5 strokes is 14%. 6 strokes, 5%. 7 strokes, 4%. And 8 strokes is 1%. So I'm just going to add together those 5 numbers. So 40 plus 14, 54, plus 5, 59, 63, 64. Okay, 64%. And if we add that to 11 and 25, it should all total up to 100%. If it doesn't, then there was something that was left off of this chart here. So 64 plus 11 is 75, plus 25 is 100. So yes, they all add up to 100. All right, that's it for this homework, and I'll see you again in class.